This Python code installs or upgrades the TensorFlow library using the pip package manager. TensorFlow is an open-source machine learning framework that's used for a variety of applications, including deepfake detection. The at the beginning allows this command to be run in a Jupyter notebook or similar interactive environment. The -u or upgrade option ensures that if TensorFlow is already installed, it will be upgraded to the latest version available. This Python code appears to import a set of libraries that are commonly used for data science and machine learning tasks, with a specific focus on deepfake detection. Sys provides access to some variables used or maintained by the interpreter and to functions that interact strongly with the interpreter. Sklearn, an abbreviation for scikit-learn, it is a machine learning library that contains various tools for data mining and data analysis. TensorFlow, an open-source library for numerical computation and machine learning, particularly deep neural networks. CV2, the OpenCV library for computer vision tasks, which includes capabilities for image and video analysis. Pandas, a data manipulation and analysis library that offers data structures and operations for manipulating numerical tables and time series. NumPy, a package for scientific computing that provides support for arrays and matrices, along with a collection of mathematical functions to operate on these data structures. Plotly.graphObjs and Plotly.offline.iplot, components of the Plotly library, which is used to create interactive plots and figures for data visualization. Matplotlib.pyplot, a plotting library that is often used to generate 2D graphics and plots. Although the code block solely consists of import statements and doesn't perform any operations, it suggests that the larger script or application of which this code is a part likely engages in deepfake detection by analyzing visual data using CV2, manipulating and analyzing data using Pandas and NumPy, employing machine learning algorithms Sklearn and TensorFlow, and visualizing results Plotly and Matplotlib. The Python code tf.test.isGPUAvailable is a TensorFlow function that checks if a GPU is available on the machine where the code is being executed. Specifically, it is used to determine if TensorFlow can access a GPU to accelerate deep learning computations, which is particularly relevant for tasks like deepfake detection that require significant computational resources. If a GPU is available, the function returns true, otherwise it returns false. This function is part of TensorFlow 1.x and may be deprecated in TensorFlow 2.x, which uses different functions and methods to check for GPU availability. The code tf.scoreVersion in Python is used to check the version number of the TensorFlow library installed in the current environment. TensorFlow is an open-source machine learning library used for various applications like deepfake detection. This code snippet will simply print out the version of TensorFlow that is being used. This Python code snippet configures the styles of various elements of plots generated using the Matplotlib library. It sets a default font size for text, sizes for axis labels and titles, and adjusts the font size for legend text and tick labels on both X and Y axis. This would affect all subsequent plots created with Matplotlib in the same script or session, making them use these specified style settings for a consistent look, which could be particularly useful for presentations or publication quality figures. This Python code defines a function getData that reads a CSV file named metadata.csv from the directory /input/faces using the pandas library implicitly assumed to be imported as PD and returns the resulting data frame. This function could potentially be part of a larger script for loading data that will be used in deepfake detection analysis. This Python code snippet calculates and returns the number of entries labeled as fake and the number of entries labeled as real within the metadata set, which is likely a data frame. It uses Boolean indexing to filter rows by the value in the label column and count them. This Python code is designed to create a balanced dataset of real and fake samples, which can be used for training a deepfake detection model. The dataset is presumably stored in a data frame meta with a column label that specifies whether each entry is real or fake. 1. It first filters the meta data frame into two separate data frames, real DF containing only the real examples and fake DF containing only the fake examples. 2. It then randomly selects 8,000 samples from each of the real and fake data frames using the .sample method, ensuring reproducibility by setting a random state equal 42. 3. Finally, it combines these two sampled subsets back into one data frame sample meta using pd.concat, which now has an equal number of real and fake samples and a total of 16,000 samples for use in deepfake detection. This Python code splits a dataset of sample metadata into three parts: a training set, a validation set, and a test set. It uses the train test split function from the sklearn.modelSelection module to perform the splits. Initially, it splits the sample metadata set into a training set, 80% of the data, and a test set, 20% of the data, stratifying the split based on the label column to maintain the proportion of classes. Then, it further splits the resulting training set into a new training set, 70% of the initial training data, and a validation set, the remaining 30%, again stratifying based on the label column. The random state equals 42 ensures reproducibility by setting the random seed. The code snippet trainset.shape, valset.shape, testset.shape accesses the shapes of three datasets, trainset, valset, and testset, which likely represent the training, validation, and test sets used in a deepfake detection model. The .shape attribute of these datasets returns the dimensions of each set, indicating the number of samples and features or data points they contain. This information is useful to understand the size and structure of the datasets before feeding them into a machine learning model for training and evaluation. This Python code is creating a bar chart to visualize the counts of real and fake labels in training, validation, and test datasets. It's using Plotly for plotting, where go.bar creates bar chart traces for real and fake counts separately. These counts are determined by summing the number of real and fake labels in trainset, valset, and testset. The resulting bar chart is displayed using iPlotfig, showing the distribution of real and fake labels across the three datasets. This Python code snippet is creating and displaying a grid of images with labels indicating whether they are real or fake. Specifically, it is 1. Setting up a figure with a size of 15 by 15 inches using matplotlib.pyplot aliased as PLT. 2. Iterating over a subset of indexes from the train set from the 26th to the 50th element. 3. For each iteration, it configures a subplot within a 5 by 5 grid without ticks on the x and y axes and no grid lines. 4. It reads images from a specified directory using cv2.imread with the image file names constructed from trainset and adds the .jg extension. 5. It uses pl.imshow to display these images in the subplots. 6. It sets the x-axis label to fake image or real image depending on the label column value in trainset for each corresponding image. 7. Finally, it uses plt show to display the figure with the plotted images. This is typically used in deepfake detection to visualize and manually inspect a set of images for authenticity. This Python function named retrieveDataset is designed to process a dataset for deepfake detection by loading images and their corresponding labels into separate lists, which are then converted into NumPy arrays before returning. It iterates over pairs of video names and labels from the setName argument, reads each image using OpenCV's imread function from a specified directory, appends the image to the images list, and appends a label value to the labels list, where fake images are labeled with 1 and real ones with 0. The image paths are constructed by removing the last 4 characters of the video name, likely its file extension, and appending .jpg to form the complete path to the image file. The function finally returns the images and labels as NumPy arrays. The code snippet retrieves and assigns training, validation, and test datasets along with their corresponding labels for deepfake detection. The retrieveDataset function is called with different dataset identifiers, trainset, valset, testset, and returns 2 items each time. The dataset inputs x and the expected outputs or labels y. These are respectively assigned to the variables xtrain, ytrain for training data, xval, yval for validation data, and xtest, ytest for test data. This Python code defines a convolutional neural network CNN using TensorFlow's Keras API, which could be used for binary classification tasks such as deepfake detection. It sets a fixed seed for random number generation to ensure reproducibility, creates a custom convolutional layer with predefined parameters using partial, and then builds a sequential model consisting of several convolutional layers, max pooling layers, a flattening layer, dense fully connected layers with dropout for regularization, and an output layer with a sigmoid activation function for binary classification. The network takes input images of size 224 by 224 with 3 color channels. This Python code snippet is configuring a machine learning model for the training process in the context of deepfake detection. The model.compile method sets up the model with the following parameters. 1. Loss equals binary cross entropy. This defines the loss function to be binary cross entropy, which is a common choice for binary classification problems like deepfake detection, where each input is classified as either real or fake. 2. Optimizer equals NADAM. NADAM is an optimization algorithm used to update the model's weights based on the data it sees and the loss it's trying to minimize. 3. Metric accuracy. This tracks the accuracy metric during training, which is the percentage of correctly classified instances. Finally, model.summary prints a summary of the model architecture, providing details about the layers, their shapes, and the number of parameters. This helps to understand the model structure before the actual training begins. This code trains a machine learning model using training data. Specifically, it feeds the training input data xtrain and the corresponding labels ytrain to the model for a total of 5 training iterations, known as epochs. During training, the model uses mini batches of 64 samples at a time. It also evaluates the model's performance on a separate validation dataset, consisting of xval and yval, to monitor its accuracy on data it hasn't seen during the training process. The history variable captures the performance metrics of the model for each epoch, such as loss and accuracy for both the training and validation datasets. This process is part of training a deepfake detection system to distinguish between real and synthetic media. This line of Python code evaluates the performance of a machine learning model on a test dataset. The model.evaluate method calculates the loss and any additional metrics like accuracy, if defined on the data provided by xtest features and ytest true labels. The score variable stores the result of this evaluation, which could be used to assess the model's ability to detect deepfakes, assuming model is a deepfake detection model. This Python code plots the performance of a model used for deepfake detection over a series of training epochs. It generates 2 graphs. The first graph shows the training accuracy and validation accuracy over the epochs, and the second graph shows the training loss and validation loss over the same period. The graphs are displayed side by side for easy comparison using subplots, with labeled axes and legends for clarity. The plt show command at the end displays the plotted graphs. This Python code creates TensorFlow datasets for training, validation, and testing from existing arrays of data features and labels. Xtrain, ytrain represent training features and labels, xval, yval for validation, and xtest, ytest for testing. These datasets can be used for building and evaluating a deepfake detection model. The Python code snippet is preparing datasets for training, validation, and testing in a deepfake detection system using TensorFlow's Keras API. It does the following. 1. Clears the Keras session to remove any existing model or layer configurations. 2. Sets a batch size of 32 for processing multiple images in each iteration. 3. Applies a preprocessing function from the exception model to the datasets, casting the input data to float32 type. 4. Shuffles the training dataset with a buffer size of 1000 and sets a fixed seed for reproducibility. 5. Batches the training dataset into the specified batch size and uses prefetch1 to ensure that data loading does not become a bottleneck. 6. Batches the validation and test datasets similarly, but without shuffling. This Python code visualizes the first 9 images from the first batch of a validation dataset, valid set. It displays each image in a 3x3 grid with their corresponding class labels fake if ybatch index is 1 or real if it's 0, after rescaling the image data to a 0 to 1 range for proper rendering by plt.imshow. The axes are turned off for a cleaner look. This visualization is likely used for evaluating a deepfake detection model's performance on the validation set. The Python code creates a data augmentation pipeline using TensorFlow's Keras API that consists of 3 layers designed to randomly augment images as part of preprocessing for deepfake detection. 1. Random flip flips images horizontally with a set random seed for reproducibility. 2. Random rotation rotates images by a random amount, up to 5% factor 0.05 of 360 degrees, again with a set seed for consistency. 3. Random contrast adjusts the contrast of the images randomly by a factor of up to 20% factor equals 0.2 with the same seed for reproducibility. This augmentation helps in simulating different variations of input data, potentially improving the robustness of the deepfake detection model. This Python code snippet is for visualizing the first 9 images from a validation set after they have been augmented using a data augmentation function, specifically within the context of deepfake detection. It takes a batch of images with their corresponding labels xbatch, ybatch from the validation set valid set, applies the data augmentation on the images xbatch core augmented, and then displays these augmented images in a 3x3 grid plot. Each subplot title indicates whether the original image is fake or real based on its label ybatch. The images are rescaled to the 0-1 range for display purposes using imshow and clipped to this range to ensure that any out-of-bounds values resulting from augmentation like contrast adjustments don't cause issues with the display. This Python code sets up a neural network for binary classification, e.g., detecting whether an image is a deepfake or not, using TensorFlow's Keras API. 1. It sets the random seed to 42 to ensure that the results are reproducible. 2. It initializes base model with the pre-trained exception model loaded with ImageNet weights, excluding the top fully connected layers include top equals false. 3. It applies global average pooling to the outputs of base model. 4. It adds a dense layer with one neuron and a sigmoid activation function to produce a probability output, the likelihood that the input image is a deepfake. 5. It creates the final model by linking the base model's input to the newly added output layer. This Python code snippet iterates over the layers of a pre-trained model base model and sets their trainable attribute to false. This action freezes the weights of those layers, meaning they will not be updated during further training. This technique is commonly used in transfer learning to keep the features learned from the original training dataset intact, while you train a new model, for example, for deepfake detection on top of it with your specific dataset. The provided Python code is configuring and initiating the training process for a deep learning model in TensorFlow, with the intent of possibly using it for deepfake detection. Specifically, 1. Optimizer. An SGD stochastic gradient descent optimizer is created with a learning rate of 0.1 and momentum of 0.9. This optimizer will be used to update the model's weights during training to minimize the loss. 2. Model.compile. The model is compiled with binary cross-entropy loss suitable for binary classification tasks such as deepfake detection using the previously defined SGD optimizer and will track the accuracy metric during training. 3. Model.fit. The model is trained using the train set dataset, validated using the valid set dataset, and the training will run for 3 epochs iterations over the entire dataset. The history object will capture the loss and accuracy metrics for analysis after training. This Python code iterates over tuples of indices created by zipping together 4 ranges that divide the range of numbers from 0 to 132 into 4 equal parts. For each tuple of indices, it prints the index and the name of the corresponding layer from a model named base course model. The layer names are printed in columns for comparison, with the index and layer name formatted for alignment. This could be used in deepfake detection to display information about layers in a neural network at specific intervals to understand the architecture or for debugging purposes. The Python code snippet model.evaluate test set is likely used to evaluate the performance of a pre-trained model on a set of test data, test set. In the context of deepfake detection, the model would be assessing how well it can differentiate between real and synthetic deep images or videos. The evaluate function typically returns the loss value and metrics like accuracy computed on the test set, providing an indication of the model's generalization capabilities. This Python code snippet is configuring and training a neural network model for an unspecified number of iterations epochs. Specifically, it's taking a pre-existing base model and setting the layers from the 56th layer to the end as trainable, which means their weights will be updated during the training process. An SGD stochastic gradient descent optimizer is created with a learning rate of 0.01 and a momentum of 0.9, which will be used to update the weights of the trainable layers during training by minimizing the binary cross-entropy loss suitable for a binary classification problem. The model.compile statement prepares the model for training by specifying the loss function, optimizer, and metrics to track in this case, accuracy. The model.fit function trains the model on a train set, evaluates its performance on a valid set, and does this for 10 full iterations through the dataset epochs. The model's progression is captured in the history object, which typically contains the loss and accuracy values per epoch for both training and validation datasets. This code is part of a deepfake detection system, where the neural network is likely fine-tuning its parameters to better differentiate between genuine and fake images or videos. This Python code generates 2 plots to display the performance of a machine learning model over training epochs. The first plot shows the accuracy of the model on both the training and validation datasets across the epochs. The second plot shows the loss or error of the model on both the training and validation datasets across the epochs. It helps in visualizing how the model's performance improves with each epoch and in assessing overfitting or underfitting by comparing training and validation metrics. This line of Python code evaluates the performance of a trained model on a test dataset referred to as test set. Specifically, in the context of deepfake detection, it would provide metrics such as accuracy, loss, or other relevant measures that indicate how well the model can identify deepfakes when presented with previously unseen data. This Python code line saves a trained machine learning model, specifically a model that might be based on the exception architecture, to a file named exception_deepfakeimage.h5. The file format .h5 indicates the model is being saved in HDF5 format, which is a binary file format commonly used for storing large numerical models. This allows the model to be loaded later for further use, such as for deepfake detection tasks. The code pip install lime is not actually a Python code snippet, but rather a command line instruction known as a magic command used in Jupyter notebooks and similar interactive computing environments. This command installs the lime local interpretable model agnostic explanations Python library, which is used for explaining machine learning model predictions. In the context of deepfake detection, lime could be used to interpret why a model predicts a particular video or image as being real or a deepfake by providing explanations for the model's decisions in a human understandable form. This Python code initializes an object called explainer, which is an instance of lime image explainer from the lime library. This object is used for explaining predictions of image classifiers in a way that humans can understand, by identifying regions in the image that are important for making a prediction. It is particularly part of a deepfake detection system, where it might help highlight areas of an image that contribute to whether the system thinks the image is a deepfake or not. This Python code snippet is used for visualizing a set of images in a 3x3 grid format using matplotlib, a plotting library. Each image retrieved from the array X is normalized from a range that perhaps is -1 to 1 due to X index plus 1, 2, to a range suitable for display 0 to 1, and then displayed. The title of each subplot indicates whether the image is classified as fake or real based on the corresponding value in the array Y. If Y index is 1, the image is labeled fake. Otherwise, it's labeled real. The axes are turned off for a cleaner look. The pel.show function is called to display the plot once all subplots have been configured. This code likely serves the purpose of evaluating or demonstrating the performance of a deepfake detection algorithm by presenting examples of real and fake images. This Python snippet selects a subset of data from a multidimensional array X and assigns it to the variable test data. It extracts the third element index 2, considering zero-based indexing along the 0th axis of X, and includes all elements along the remaining axes. Then testData.shape is likely called to retrieve the dimensions of the resulting test data array, which would be useful information in the context of preparing or analyzing data for deepfake detection. This Python code uses an explainer to interpret a machine learning model's prediction on a given instance of test data, likely for the purpose of deepfake detection. The explain instance method takes the test data converted to double precision floating point format, passes it through the model's predict function to generate predictions, and then explains those predictions. It focuses on the top 3 predicted labels, most likely classes the model thinks the test data belongs to, possibly obscuring certain features by setting them to a hide color value 0 here, and bases the explanation on a sample of 1,000 perturbations of the input data. The result, stored in the explanation variable, will help understand why the model made its decision, making the model's predictions more interpretable. This Python code uses a library for image segmentation to visualize important regions of an image that contribute to a deepfake detection algorithm's decision. First, it obtains 2 variants of the image and corresponding masks using a method getImage and mask, one with only the positive contributions of the top predicted label, limited to 5 features and hiding the rest of the image, and another considering both positive and negative contributions with 10 features and showing the whole image. It then creates a figure with 2 subplots and uses mark boundaries to overlay the obtained masks onto the original images, indicating important areas for the prediction. These are displayed in 2 axes, side by side, without axis labels for a cleaner look. This command is used to install or upgrade TensorFlow, which is an open-source machine learning library, to the latest version. The command is run in a notebook environment, often Jupyter or Google Colab, that supports shell commands prefixed by an exclamation mark. The U or upgrade flag ensures that TensorFlow is upgraded to the latest version if it is already installed. This Python code snippet imports various libraries and modules that are used for deepfake detection in an image processing or machine learning context. Specifically, TensorFlow docs.viz.embed, a visualization utility from TensorFlow's documentation tools for embedding multimedia, like videos, in notebooks. Keras, a high-level neural networks API running on top of TensorFlow for building and training deep learning models. Matplotlib.pyplot, a plotting library for creating static, animated, and interactive visualizations in Python. TensorFlow, the core TensorFlow library for machine learning and artificial intelligence. Pandas, a data manipulation and analysis library. NumPy, a library for numerical computing with Python. Imagio, a library for reading and writing images. CV2, the OpenCV library for computer vision tasks. OS, a standard library module for interacting with the operating system. Overall, the code is likely setting up the necessary environment to process images, possibly videos as well, train a machine learning model to detect deepfakes and visualize the results. However, without the actual processing, training, and visualization code, this is just preparatory setup. The code is used to count and print the number of video files in two separate folders, one for training samples and one for test samples. These folders are part of a dataset for a deepfake detection challenge. It displays the quantity of files for each folder, which are located within a common data directory. This Python code loads a JSON file named metadata.json from the specified directory /input deepfake detection challenge /train sample videos into a pandas data frame. It then transposes the data frame with the .t method so that what were originally JSON keys become the data frame's index, and the associated values become the data frame's columns. Lastly, it displays the first 5 rows of the data frame using the head method to get a quick preview of the data, which is related to a deepfake detection task. This Python code generates and displays a bar chart that visualizes the distribution of different labels classes in the training data for a deepfake detection task. It first groups the training sample metadata by the label column, counts the occurrences of each label, and then creates a bar plot with a specified figure size of 15 by 5 inches, adding a title to the plot. Finally, plt.show is called to display the plot. The Python code train sample metadata.shape accesses the shape attribute of a variable presumably named train sample metadata. This variable likely represents a dataset or a two-dimensional array-like structure that is part of a deepfake detection system. The .shape attribute is commonly used with arrays, pandas data frame objects, or similar data structures to return a tuple representing the dimensions of the array or data frame. In other words, calling .shape will give you the number of rows and columns in the data structure. So the code snippet you've provided would simply return the size of the train sample metadata in terms of the number of samples, rows, and features columns contained within it. This could be used to understand the structure of the training dataset for deepfake detection. The code snippet selects 3 random indices from the train sample metadata data frame where the label column is fake. It creates a list of these indices and stores it in the fake train sample video variable. This is likely used to sample 3 fake videos for deepfake detection training purposes. This Python code defines a function called displayImageFromVideo that takes a video path as input and does the following. 1. Initiates video capture from the specified video path. 2. Reads the first frame image from the video. 3. Converts the color format of the frame from BGR to RGB since OpenCV uses BGR by default, but Matplotlib expects RGB. 4. Creates a Matplotlib figure and displays the color-corrected frame within it. The code is part of a deepfake detection process, presumably for visually inspecting frames from videos to detect signs of manipulation. This Python code snippet iterates over a list of video file names fake train sample video, and for each video file, it calls the function displayImageFromVideo with the full path to the video file as an argument. The full path is constructed by joining a data folder path, data folder, a training samples folder, train sample folder, and the current video file name video file. The purpose in the context of deepfake detection is to display images from a sample of videos labeled as fake for further analysis or review. This Python code selects 3 random video entries labeled as real from a dataset containing metadata for training samples. It then stores the indices of these selected videos in a list called real train sample video. The dataset is likely part of a collection used for deepfake detection, and these real labeled videos are probably genuine videos used to train a model to distinguish between real and fake content. This Python code snippet is designed to display images from a collection of video files that are used for training a deepfake detection system. For each video file in a list named real train sample video, it constructs a full file path by joining a data folder, a training sample folder, train sample folder, and the name of the current video file, video file. Then it displays an image from the video using a function displayImageFromVideo. The code snippet is extracting value counts of unique entries in the original column of the data frame train sample metadata, and then it selects the top 5 most frequent entries. It is likely being used to analyze the distribution of original videos from which deepfakes might have been generated as part of a deepfake detection pipeline. The given Python code defines a function displayImageFromVideoList that takes a list of video file paths, video path score list, and an optional video folder argument specifying the base directory of these videos. The function displays the first frame image from each of the first 6 videos in the list. It does this by capturing the video, reading the first frame, converting its color space from BGR to RGB, and then plotting it on a 2x3 grid of subplots using Matplotlib's plotting library. Each image is labeled with the corresponding video's file name. The path to the video files is constructed by joining the data folder, and video file name. The axis on command for each subplot is likely meant to be axis off to hide the axes for a cleaner display of only the images. This Python code snippet is likely part of a larger deepfake detection system. It selects and displays images from a list of videos in a training dataset that are associated with the original video file named atmxv.wins.mp4. The train sample metadata is presumably a data frame that contains metadata about training samples. The code filters this data frame to find all entries with the original column matching atvmxvins.mp4, gets the index of these entries, and stores them in a list. This list, same original fake train sample video, is then passed to a function display image from video list, which presumably displays images from the videos in that list. This line of Python code creates a pandas data frame called test videos. It populates this data frame with the file names of all the files in the directory specified by the path os.path.joinDataFolder test folder. The file names are listed in a single column named video. Essentially, this is used to prepare a list of video files, presumably for further processing in a deepfake detection task. The Python code testvideos.head is likely calling the head method on a data frame named testvideos. This method, when used on a pandas data frame, returns the first few rows by default, the first 5 rows of the data frame for quick examination of the dataset. The context suggests that test videos contains data related to test videos used in a deepfake detection task. The given Python code snippet calls a function named displayImageFromVideo with a single argument that is a constructed file path. This function presumably displays an image extracted from a video. The file path is created using the os.path.join function, which combines data folder, test folder, and the file name of the third video iloc2, video from the test videos data structure. iloc2 implies it is accessing the third item in test videos using index-based selection. The data folder and test folder are variables that likely hold the names of directories, and test videos.iloc2. Video suggests that test videos is a pandas data frame or similar structure with a column video that contains the names of video files. The code is part of a deepfake detection system, so the function displayImageFromVideo is possibly used to show a frame from a video file for visual inspection or further processing in the context of identifying manipulated or synthetic media content. This line of Python code selects all the rows from a data frame train sample metadata where the label column has the value fake. Then it retrieves the indices of these rows and creates a list called fake videos. Essentially, it generates a list of indices corresponding to fake videos in the training sample metadata. The provided Python code defines a function playVideo that takes in the name of a video file and the folder where it is stored, and returns HTML code to display the video within a Jupyter notebook. It reads the specified video file, encodes it in base64 to embed it directly into the HTML, and sets up a video player of width 500 pixels with controls to play, pause, etc. The last line of the code calls the playVideo function to display the 11th video from a list of fake videos 10, considering 0 indexing. This is used in the context of deepfake detection, likely to visually inspect the videos. The Python code snippet defines several constants that are likely used to configure a machine learning model or data processing for deepfake detection. IMG size, the size, height, and width to which input images are to be resized, likely before being fed into a neural network. Images will be resized to 224 by 224 pixels. Batch size, the number of images or data samples to be processed at once during training or inference. The model will process 64 images per batch. Epochs, the number of times the entire dataset is passed forward and backward through the neural network during training. The model will be trained for 10 complete passes of the dataset. Max seq length, possibly the maximum number of frames, time step, or sequence length to consider for each video or sample, depending on the context. It is likely used in sequence processing or time series data, indicating 20 time steps per sequence. Num features, the number of features to be extracted from each frame or part of the data, or the dimensionality of the feature vector. After processing, each sample will be represented by a feature vector with 2048 elements. This Python code defines 2 functions for processing video frames, typically used for deepfake detection. 1. Crop center square frame takes a single frame as input and crops it to a square shape by finding the smaller dimension of the frame, either width or height, then creating a new frame centered around the middle of the original one with dimensions equal to the smallest side. 2. Load video path, max frames equals 0, resize equals img size, loads a video from the provided path up to a specified maximum number of frames, max frames. It captures frames one by one, crops each to a square using crop center square, resizes it to a specified size, img size, and then adjusts the color channels from BGR to RGB, the order used by OpenCV, to its reverse, which is commonly used in other libraries. The frames are collected into a list, converted to a NumPy array, and returned. The video capture is properly released after processing. This Python code defines a function build feature extractor that creates a feature extractor model using the Inception v3 architecture pre-trained on the ImageNet dataset. The model is adapted to use average pooling and is set up to process input images of size img size 3, where img size is a predefined constant representing the height and width of the images, and 3 is the number of color channels, RGB. The feature extractor excludes the top final classification layer of the Inception v3 network, making it suitable for feature extraction rather than end-to-end classification. The preprocess input function is applied to the input data to prepare it for being fed into the Inception v3 model, following the same preprocessing steps that were used for the ImageNet data. Outputs from the feature extractor are the result of the average pooling layer. Once defined, the function build feature extractor is called to instantiate the actual feature extractor model, which can be used in subsequent deepfake detection tasks to convert input images into feature vectors. The provided Python code defines a function prepare all videos that processes a set of videos for deepfake detection. It takes two arguments: df, a data frame containing video metadata with labels, and root dir, the directory containing the video files. Here's what the function does. 1. It reads video paths and labels from the data frame df and converts the fake labels to binary. 2. It initializes two arrays, frame masks and frame features, to store Boolean masks indicating the presence of video frames and to store extracted features from the videos, respectively. 3. It iterates over each video, loading its frames and extracting features from each frame up to a defined max CQ length, ensuring that videos with more frames are truncated and shorter ones are padded. 4. It uses a feature extractor to predict features from each frame, storing these features and masks in the pre-initialized arrays. Finally, it returns these arrays' frame features and frame masks, along with the binary labels, indicating if a video is fake or not. This data will likely be used as input for a sequence model for deepfake detection. This Python code snippet splits a dataset into a training set and a test set. The trained sample metadata is the data being split, and the split ratio is such that 10% of the data is allocated to the test set, test size equals 0.1, and the rest to the training set. The split is done in a stratified manner, ensuring that the proportion of the different classes' labels is maintained in both the training and test sets. Stratify equals trained sample metadata, label. The random state is set to 42 for reproducibility of the split. Lastly, it prints out the shapes, number of samples, and features of the training and test sets after the split. The Python code prepares training and testing datasets for deepfake detection by calling a function prepare all videos with two parameters: a set of videos, either train set or test set, and a string indicating the type of the set, train or test. It outputs the shape dimensions of the frame features and frame masks within the training set, giving an idea of the data structure being used for model training and evaluation. This Python code defines a sequential model using Keras API for detecting deepfakes by analyzing sequences of frame features. It constructs a model with two GRU-gated recurrent unit layers to process temporal data across frames, utilizes a dropout layer to prevent overfitting, and employs dense layers with RealU and sigmoid activations for classification. The model uses a binary cross-entropy loss function, the atom optimizer, and measures accuracy. The use of a mask allows the GRU to handle varying sequence lengths by ignoring certain time steps. The model is summarized to display its architecture. This Python code snippet is configuring and running the training process for a machine learning model using the Keras library with the purpose of deepfake detection. It sets up a callback to save the model's weights only, not the full model, at the path _/ whenever it achieves the best performance on the validation set, denoted by save best score best only equals true. Then, it starts training the model.fit using a set of training input data, train data, and labels, train labels, validating against a separate test dataset, test data, test labels. It uses the specified callback to save the model weights during the training process, runs for a predefined number of epochs, and processes the data in batches of 8 examples. The provided Python code is designed to predict whether a video is fake or real as part of a deepfake detection system. Here's a brief breakdown of its functionality. 1. Prepare single video frames. This function prepares the video frames for prediction. It initializes frame masks and feature arrays. It then extracts features from each frame using a predefined feature extractor up to a max sequence length max seq length and updates the masks accordingly. Sequence prediction path. This function loads a video from a given path, processes it using prepare single video, and then passes the processed frame features and mask to a model's predict method to get the prediction. 3. To GIF images. This utility function converts a sequence of images into a GIF file for visualization. 4. The last part of the code performs the actual deepfake detection. It selects a test video at random, uses the sequence prediction function to predict whether it's fake or real, prints out the prediction, and plays the video. If the prediction probability for the video being fake is 0.5 or higher, it's classified as fake. Otherwise, it's classified as real.